Hi everyone. We're going to continue 8.2 transformations of logarithmic functions. Okay, so let's do a little bit of review. Start up on remembering what is a logarithmic function, how does it behave, and we'll talk about transformations. Okay, hot off the heels of doing transformations in exponential functions and also just from function transformations. Okay, start up. If the point -2, 25 is on the graph of y equals c of x, y equals c to the x, where c is greater than 0, then a point that would lie on the graph of y equals log base c of x is AB. Okay, the value of AB respectively are 25, -2. So I'm going to add this note, recall y equals log base c of x can be written as x equals c to the y, right? Remember our converting logarithms. This, remember, is the inverse of y equals c to the x. So if this is a point on y equals c to the x, then these two are points on the graph of y equals log base c of x, okay? Just remembering that the logarithmic functions are inverses of their exponential form, okay? Transformations of logarithmic functions. So review chart here. Here's the general transformation model for logs. Y equals a times log base c of in square brackets b times x minus h, close those square brackets, plus k. So this should look super familiar from when we did exponential transformations and just generalized function transformations in unit 1. Okay. Parameter a, vertical stretch by a factor of absolute value of a about the x-axis. Okay, mapping notation, xy becomes x, comma, ay. B, horizontal stretch by a factor of 1 over the absolute value of b about the y-axis. xy becomes x divided by by. Remember, the b value is not your factor. You have to do this thing to get the factor. Okay. H value, horizontal translation, h units right or left, xy transforms or maps to x plus h comma y, and k, vertical translation, k units down, xy becomes x comma y plus k. So when you tie all this together, what do you get? X over b plus h comma ay plus k. Okay, get used to this and this as we go through these examples. Example 1, describe the transformations on the graph of y equals log base 2 of x to become y equals log base 2 of 5 times x plus 2 plus 3. Okay, let's break this down. I'm going to write the general transformation model for logs here. Y equals, oh, come on. Y equals a log base 2, a log base c of b times x minus h plus k. Okay, I like to stack these equations up so I can see what is going on. I have a b value. First off, a value of 1. Okay, no vertical stretch. Okay, a value of 1. B value equal to, well, right here, 5. That is a horizontal stretch about the y-axis by a factor of 1/5. Remember the b value, the factor is 1 over the absolute value of b. That's 1 over the absolute value of 5. And that's how we get 1/5. H equals, well, x minus h, x plus 2. Well, that means it's x minus -2. So h equals -2. This is a horizontal translation, 2 units. It's negative, so it's 2 units left. Okay, k equals, well, it says plus k plus 3. Well, easy peasy. So k equals 3. That is a vertical translation. 3 units. Well, it's positive, so it's up. Okay. What is my mapping? So mapping x, y goes to x divided by b, which is 5. 2 units left, so it's minus 2. And then 3 units up, which is y plus 3. Okay. Where did the point 1, 0 go? Where did point 1, 0 on the original graph map to on the transformed graph? So I have x, y on the original, that's 1, 0. So right there, 1, 0. Okay, that map to, so here's our mapping, x divided by 5 minus 2. X divided by 5 minus 2, comma, y plus 3. So when I transform that, that's 1/5 minus 2, 0 plus 3. Well, what does that turn into? Negative 9/5 and 3. So there's a horizontal and vertical translation and a stretch, so it's going to pull that point all the way to negative 9/5, which is negative 1.8, so negative 1.8 and 3, so right there. So 1, 0 transforms to negative 9/5 and 3. Okay, there you go. We answered letter B. Let's go to letter C. State the equation of the vertical asymptote on y equals log base 2 of 5 times x plus 2 plus 3. Okay, so if we normally, when we have this y equals log base 2 of x, the vertical asymptote is at x equals 0. If we translate it 2 units left, well, that vertical asymptote's also going to translate 2 units left. So the vertical asymptote for this transform function is x equals negative 2 because of h value equals negative 2. Okay, state the domain and range of the transform graph. Okay, domain x such that x is, okay, greater than negative 2. Okay, you see that horizontal asymptote, oh sorry, see the vertical asymptote? That's x is an element of all real numbers. Okay, and then the range is y such that y is an element of all real numbers. Algebraically determine the x and y intercepts. So x-intercept, this is where y equals 0. Let's take our transform function. Okay, there it is. And I'm going to do a calculation for our x-intercept first. Okay, so I'm going to plug in y equals 0. I get log base 2 of 5 times x plus 2 plus 3. Let's subtract 3 from both sides. Okay, folks, I'm going to use the properties or the, I'm going to convert my logarithmic form into an exponential form. So that's take the base, apply the exponent. Okay, and then the argument is the result. So that's 1/8 equals 5x plus 10. Okay, so 10 is 80/8. Okay, that's negative 79/8 equals 5x. I'm going to divide both sides by 5. So that's negative 79. 8 times 5 equals x. And then folks, let me turn that into a decimal value. I'm going to grab my calculator real quick. That is negative 79 divided by 40. I get negative 1.975 equals x. Or negative 79/40ths in exact form. Okay. Y-intercept. This is where x equals 0. So let's start with a transform function, log base 2 of 5 times x plus 2 plus 3. Okay. And then y equals, let's make x 0. So that's 10 in the brackets here plus 3. Okay, and then this one, I'm not going to get an exact value, so let's just do use your calculator and calculate log base 2 of 10, and then add 3 to that. And then to the nearest thousandth place, 6.322. So that's your y-intercept. Okay, folks, next page. Okay, folks, example 1, we start with our base function log base 2 of x. And then if I overlay the red one on top, right? Let's look at each of our transformations. So first, the a value is 1, so there's no vertical stretch about the x-axis, but I have a b value of 5, which is horizontal stretch by a factor of 1/5 about the y-axis. So when I do a b value of 5, watch the x values. I'm going to divide all the x values by 5, right? So let's go to 5. Okay, so let's pick a point here. So I know on y equals log base 2 of x, if x is 8, then y is 3, right? So when I have a horizontal stretch, b value 5, horizontal stretch by a factor of 1/5 about the y-axis, then I should do 8 divided by 5, which would be 8/5, or what is that approximately? So 8 divided by 5, I should get about 1.6. So Desmos is showing right about there as 1.6, right? So from here, that's about 8.3 till about 1.63. Okay, so there's the b value 5. H value of -2, so horizontal translation 2 units to the left. So -2, there it is. Okay, and then a k value 3, vertical translation 3 units up. K value of 3. K value of 3, and it's going to take it up, up, up. And there we go. Okay, so one of the points that we use mapping notation to transform it, remember xy becomes x divided by 5 minus 2 comma y plus 3. So that's the mapping notation. So on our base function y equals log base 2 of x, the point 1, 0 on the base function becomes -9/5 3. So -9/5 and 3. So right about there.
know if you can see that it shows up. It's really hard to say. Negative 1.83. So 9/5 would be negative 1.8, right? 9 divided by 5. Yep, negative 9/5. And there's our transform point. The other thing, just to verify, remember we calculated a y-intercept 6.322 on the transform function. There it is right there. The x-intercept is negative 1.975. We also calculated that in our example, and there it is.
Okay, more on transformations. Sketch the graph of y equals log base 3 of x. Use transformations to sketch the graph of the function y equals log base 3 of x minus 5 minus 4 on the same grid. Okay, first let's sketch log base 3 of x. Okay, so when x equals 0, we can't have x equals 0, so that's going to be our asymptote. So it's going to approach x equals 0, the asymptote. Let's pick conveniently 1, 0, so 1, 0. 3, 1, 1, 2, 3, 1, and then 9, 2, 3, 4, 5, 6, 7, 8, 9, 2. Okay, nice smooth graph. Okay, and that is y equals log base 3 of x. Okay, all right, transformation time. So y equals a log of b x minus h plus k. What's my h value? X minus 5. H value is positive 5. What's my k value? Plus k minus 4. Well, it's plus negative 4, so k must be negative 4. This is a horizontal translation, 5 units right. This is a vertical translation, 4 units down. So let's apply that to our point 1, 0. So we don't have any stretches or reflections. Okay, this is just two translations. So 1, 0, I'm going to add 5. So 1 plus 5 is 6. I'll do the first one here. 1 plus 5, comma, 0 minus or 0 plus negative 4. Okay, and that is 6, negative 4. Okay, let's do the other one. So 3 plus 5 is 8. 1 plus negative 4 is negative 3. And then 9 plus 5 is 14. And 2 plus negative 4 is negative 2. Okay, let's graph that in blue. So I'm going to do blue for this. So I got 6, negative 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 6, negative 4. 8, negative 3. Okay, and 14, negative 2. 9, 10, 11, 12, 13, 14, negative 2. Okay, and nice smooth graph. Oh, I'm going to stop there. Where is the vertical asymptote? Well, if I have h equals 5, so now we're starting to understand characteristics of what happens to our vertical asymptote. If we started at x equals 0 for our horizontal asymptote, and then we translated 5 units right, well, where's that vertical asymptote going to go? It's going to go 1, 2, 3, 4, 5. Right there. So be careful when you're sketching your graph. Accuracy matters here. Okay, this is y equals log base 3 of x minus 5 minus 4. Okay. Next example, use transformations to sketch the graph of y equals 2 log base 2 of negative x plus 1. Okay, first off, I have to do this, folks. You have to put it in the correct form. So remember, the correct form is y equals a times log base c of b times x minus h plus k. this is not in the correct form. Look at what you have here. The b value is separated with brackets, right? So let's separate it with brackets. Okay, so I'm going to do this. -1 times x minus 1. And then now it looks like this form. Okay. Okay. I'm going to start with this. I want to say, when I analyze this, base function is y equals log base 2 of x. Okay, and then analyze your transformations based on this base function. Okay, I see a value equal to 2. What does that tell me? This is a vertical stretch about x-axis by factor of 2. Okay, b equals -1. This is a reflection in the y-axis. X minus 1, x minus 8, so h equals +1. This is a horizontal translation 1 unit to the right. Okay. Okay, so when I graph my let's graph our logarithmic function first, the base function here, y equals log base 2 of x. Well, at x equals 0, well, we can't do that, right? That's the vertical asymptote. X equals 1, y equals 0, x equals 2. Okay, do that calculation. Y equals 1, x equals 3. Sorry, x equals 1, 2. Let me do x equals 4. Again, nice, neat integral values. So 4, y equals 2. 1, 2, 3, 4. 1, 2. X equals 8. 1, 2, 3, 4, 5, 6, 7, 8. Y equals 3. Okay, so that is our base function. Y equals log base 2 of x. Okay. What's next? In blue. Let's do this. This is going to be very difficult to graph this. It's going to be very difficult to graph this. Use the graph and then apply all these stretches and reflections. So what I'm going to do is I'm going to use mapping notation to make this nice and easy for me. Okay, so just separate page here. On the original function, y equals log base 2 of x. I have a set of points x, y, which are 1, 0, 2, 1, 4, 2, and 8, 3. Okay, and then this is transformed to y equals 2 log base 2 of -1 times x minus 1. Well, what's our mapping notation? This is good practice. That's -x plus 1. Okay, that's our h value of 1. -1 is our reflection in the y-axis. And then I have a value of 2, so that's just 2y. So I'm going to take all my points for x, y, and apply the mapping notation. And that becomes 1, So that's -1 plus 1, comma, 2 times 0, and that becomes 0, 0. Okay, next one, -2 plus 1, comma, 1 times 2, and that becomes -1, 2. Okay, so you got the idea. So I'm going to transform the rest here negative 3, 4. And this one is negative 7, 6. Okay? Now take all of these points, go back and graph it. So this is, I think, the better way, because it's going to be super hard. I mean, it's harder to do it on the graph. You can certainly do it. I'm not saying it's impossible, but I'm going to just do it this way. I feel it's a bit easier. So 0, 0, negative 1, 1, 2, negative 3, 1, 2, 3, 1, 2, 3, 4. Okay. And negative 7, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay. Where's my horizontal asymptote? Sorry, where's my vertical asymptote for the transform graph? So if I start drawing it here, folks, don't cross it. Where is it? Well, the h value is 1. Okay, so the h value is 1. So it shifts the horizontal asymptote to from 0 to 1. So x equals 1 is our equation of asymptote. So it's going to approach right there. So I'm just going to draw in, sorry, a vertical asymptote. That's x equals 1. Okay, let's fill in some characteristics and values for our transform function. Okay, identify the following characteristics. Y equals 2 log base 2 of negative x plus 1. The domain, you can see from the graph, x is less than 1. The range, still all real numbers. X-intercept, okay, that's right on 0. Y-intercept, also 0. Equation of the asymptote, x equals 1. This is because, okay, because of our h value being equal to 1, it shifted the vertical asymptote over 1 unit. Okay. This is a note about graphing. So you should have come into this lesson already knowing how to do the change of base identity, because when you're graphing something with a base 2, remember the log, the log key in your, so you have a key that on your calculator that says log. This is base 10, folks. But if you do something with a base 2, you're going to have to know how to do the change of base identity on your calculator, or most calculators now have a feature that allow you to change bases automatically just using a quick keystroke. Okay? All right. So this is a demonstration. Again, review this, but you should have come into this lesson knowing how to do this, also knowing how to graph basic functions. Okay? All right. Okay, howdy folks. We're going to continue here. Example 4. The graph of f of x equals log base 4 of x is horizontally stretched about the y-axis to obtain the graph of g of x. So here's g of x. Here is f of x. If the point, that should be 1, 1, folks, 1, 1. Okay, if the point 1, 1 right here is on the graph of g, then algebraically determine the stretch factor and then write the equation of g of x in terms of x. Okay, here is the point 4, 1. Okay, let's see what happens with this transformation. If I start with f of x at 4, 1, and I go to g of x at 1, 1, well, what sort of transformation is happening? So if we start with the original, which is xy, and I end up with 1, well, I need to divide 4 by 4 to get 1, right? So it's x value divided by 4, and then y value stays the same. It's a times 1, and the a value is 1, right? There's no vertical stretch, so it's 1. Okay, so right here, I can tell right away the b value is 4. Okay, algebraically determine the stretch factor. Remember, the factor is different than the b value, so the factor equals 1 over absolute value of b. That's 1 over absolute value of 4. So the stretch factor is 1/4. Okay, so that's part 1, is determine the stretch factor. Let's write the equation. So f of x, y equals log base 4 of x, that's our original equation, f of x, okay? When we transform it, it turns into y equals log base 4 of, so remember our general transformation model is y equals a times log base c of b times x minus h plus k. The only thing that we're changing here is the b value. Okay, so when I write this, instead of x, I'm going to replace it with 4x. Okay, and you can, so this is the final equation. You can graph these two, and check these particular test points, and you can even check this test point as well. Okay, check that one. Okay, example 5. The red graph can be generated by stretching the blue graph of y equals log base 4 of x. Okay, so this one, I'm sorry about that, that's a typo. This should be the blue graph can be generated by stretching the red graph. So if you think about what we're doing, we're generating the blue graph from the red graph. So we're doing a stretch in reverse compared to example 4. Okay, so now if I have g of x, it has the point 1, 1. F of x, what's that corresponding point? That's 4, 1. Okay, so I'm going from x, y. Well, I'm only changing my x values, folks. So that's 4x, comma, y. That's my mapping. Okay, so that is x over b, comma, y. Okay, then what is the b value? So 4x equals x over b. X's cancel, 4b equals 1, b equals 1/4. So I'm going to insert, so this is what I do. So I'm going from this time the red one, red g of x equals from here, log base 4 of 4x, and I'm making the graph f of x. F of x equals log base 4. Well, where do I insert this b value of 1/4? Right in here. And then that equals f of x log base 4 of x, and should be no surprise to you that that is the same equation that we started with in the beginning. So we're making a horizontal stretch one way, then we're going reversing the horizontal stretch. Okay. Next one, folks. The red graph can be generated by stretching and reflecting the blue graph of y equals log base 4 of x. Determine the equation that describes the red graph. Okay, so first off, I'm going to look at this vertical stretch. So we're going from red graph, so we're by stretching, reflecting the blue graph. So let's reflect the blue graph first. I'm going to do that. Remember, we can do it in either direction. So if that happens, right, that's the blue graph. So in black, this is the blue graph reflected. So reflect in x-axis. So a is less than 0. Okay, let's look at the vertical stretch factor. It looks like all we got left is a vertical stretch factor. If I'm going, so I'll put this in green. If I'm going 1 unit down to get to the black graph, how many units do I go to the red? 1, 2, 3. So it looks like it's a vertical stretch by factor of 3 about the x-axis. So a absolute value of a equals 3, but a is less than 0, therefore a equals negative 3. Okay, determine the equation that describes the red graph. So if I start with y equals log base 4 of x, and I'm transforming it with a vertical stretch and a reflection in the x-axis. Okay, I'm going to go to, let's write it in general term here. That is y equals a log base 4 of x. Well, the only thing we're doing is reflecting and vertically stretching it, so y equals negative 3 log base 4 of x. Graph this and check that it matches that. Okay? All right, last one, folks. The graph of y equals g of x is shown to the right. Determine the equation g in the form g of x equals a log base 2 of x minus h plus k. Ooh, okay. We're going from, so we need to reverse all the transformations. So remember if whatever this imaginary, whatever the starting function was, right? I'm going to assume, so let's compare to the base function. So base function. Okay, it's a base 2, right? So the base function is f of x equals log base 2 of x. Okay, let's graph that real quick. Okay, 1, 0. 2, 1. So be mindful of the units here. The scale is a little different. 4, 2. Okay, 0.25 or 1/4 and negative 2. So 1/2, 1/4, and negative 2. Okay, this is going to help you think about how do I go backwards from the transform graph to the original. This is y equals, this is f of x, okay? Let's think about it backwards. So if you think about our transformations, we usually transform an original graph or a base function using SRT, stretch, reflect, translate. If I already have a transform graph, I'm going to back everything out and start with the translations first, work backwards, and then get to our reflections and stretches. So this is kind of an advanced problem. This is a little bit more difficult, but definitely doable. Number 1. Here's some clues. Vertical asymptote at x equals negative 3. Well, what does that tell me? H equals negative 3. That's the first clue. Number 2. So this is x equals negative 3. If I move point negative 2, 1 right 3 units. So here's negative 2, 1. I'm going to move it to the right. Okay. If I move the point 1, if I move the point negative 2, 1 right 3 units, where are you? I'm at 1, 1. This is right above 1, 0. Okay, if I move this 3 units to right here, I'm exactly 1 unit above. This is right above 1, 0. This implies a vertical translation has happened of 1 unit up. This implies k equals 1. So 1 unit up. Okay? Let's keep going. 3. Point 1, 1 is now at 1, 0. So we've now brought it all the way back to 1, 0, which is on the original graph f of x, okay, or the base function f of x. 4. Now let's determine the vertical stretch. Okay, the points match up when I do the horizontal and vertical translations. Now these line up, right? 1, 0 on the transform graph and 1, 0 on the original function line up, but the key here is that the graphs don't exactly match. We need to get them to match. So what other transformations can we back out or reverse to get the original graph? So okay, so determine the vertical stretch. So it looks like a vertical stretch, and here's why. So we're going to look for the a value, right? Start with 0.57. Transform it by reversing the horizontal and vertical translation. Okay, so I'm going to back it up. So if I had h value of -3, 5.7 becomes, so I'm going to back it out. Instead of going left 3, I'm going to go +3, right? Because the transform one went left 3. I'm going to add it back. That becomes 8. And then the 7, I went 1 unit up. I need to bring it back down to match the graph. So I'm going to reverse it by subtracting 1. So I have 8.6. Okay, once I do that, where does that 8.6, this one, where does it land, right? Notice that 8.6 on transformed graph corresponds to 8.3 on f of x, the base function. Okay, now that we have a set of points as our reference, so if I have, let's call the transform function g of x, I have 8.6, and I'm going back to f of x, and it's 8.3. Let's map this. What happens? If this is x, y, how am I transforming this? X is the same, so x is going to be like that. Y, I'm dividing by 2, so it has to be 1/2. Oh, sorry. Okay, determine the vertical stretch. Translate. Okay, so we're on 0.86. 8.6 corresponds to 8.3. Okay, so let me do this. I'm going to swap positions here. Sorry about that, folks. F of x, if I started at 8.3, right? And then I'm going to g of x, right? That's 8.6. That's xy. Okay, that is x to y. Okay, so my a value is 2 to get from f of x to g of x. Okay, so let's catalog all this. H equals -3, k equals 1. Okay, and then my a value equals 2. Okay, so I need it in the form g of x equals a log base 2 of x minus h plus k. And let's fill in our values. That's 2 log base 2 of x minus -3 or plus 3, and then plus 1. Okay, again, this is quite a challenging problem where you reverse all of your transformations out. So,
Okay, folks. Let's do this. Remember in class it was a fairly difficult example where all we're given is the final product, the transform graph. And let's turn around and not only compare it to the base function, but also let's determine the equation of this transform graph. Pretty hard to do. But let's think through this logically, okay? I wrote it down here, but this is the final product. I'm going to pretend you didn't see this, right? But I just need to do that on Desmos to show you the graph. This is all you're given, right? So this would be your vertical asymptote at x equals -3, okay? One of the clues that we gave here was that it's a base 2 logarithm. So I can draw that in right there. So I did that in the class example, base 2 logarithm. And let me throw down these 3 points that are key. It'll help us compare. So that's 1, 0, 4, 2, and 8, 3. On our transform function, I have -2, 1, and 5, 7. That's all we're given, okay? One of the clues I have here is that, let me throw in this green line here. This is the vertical asymptote for this blue graph right here, right? So that's the vertical asymptote. Okay, so I'm going to throw that in there. The -3, x equals -3 vertical asymptote on the transform graph, that tells me that the h value is -3. So if I back this up, right, and I take the red graph and I move it back because the horizontal translation would have been one of the last things that we did, along with a vertical translation if there was one, right? So if we move it back, right, so we would have something like this, right? So okay, and then when I look at this, then point -2, 1 becomes 0.11, right? So 0.11 right there, right? And then this 0.10, that tells me there was also a vertical translation 1 unit up, so I'm going to reverse that, and let's go backwards. And then now we're left with that, okay? Now we need to make a comparison here. So I'm going to throw a chart here, table. Okay, so let's pay attention to this, right? One other point, I'm gonna throw back that original 0.57. Okay, here's the 0.57. Here's the 0.86. How are they related? Well, the two final transformations that I did was a horizontal and a vertical translation. 3 units left, 1 unit up, right? So if I reverse that, 3 units to the right, so 5, 7, 3 units to the right brings me to 8, and then 1 unit up, I'm going to reverse that, I'm going to go 1 unit down, it brings me to 0.86. So let's remember 0.86, and then let's figure out, we can see that there's a 2 here. Let's prove that the a value is 2. So if that's 86, folks, okay, hang on, let me just make this stick. So 8, 6. Okay, so if that's 8, 6, and this is 8, 3, the x values are the same. The y value changes by a factor of 2 going from the blue to the red. That means the a value has to be 2, right? So if I back this 2 out, it'll go exactly down there. So if I do the vertical stretch by a factor of 2, and then let me do this. I'm going to put the original points back on. Let's start with the base function. So I backed out all the transformations and I matched the original base function. Let me put in the -2 and 1. I'm going to put that in there, and I'm going to put in 5, 7. 5, 7. So I'm going to keep these 2 points in mind. I'm going to change these. Vertical stretch of 2. Horizontal translation of 3 units left, and then a vertical translation of 1 unit up. Okay, doesn't match those 2 points. You betcha right here. Let me do -2, 1, and 5, 7. And you can see it clearly matches the 2 points there. Wow, this is a hard example. Okay, this is a very difficult problem, so give it a try.